وعليكم السلام ورحمة الله وبركاته.
حياكم الله. Okay, so let's continue what we were discussing last class, just before the quiz. If you remember, over the past couple of classes, 2-3 classes or so, we have been talking about the Fourier series, and I think I've discussed it so many times, so I'm not going to go and discuss it again, okay? We need to finish at least this problem, and hopefully, if we have time, we'll also talk about other problems. Or, yeah, I may give you another problem of how we can find the Fourier series. So, if you remember, I gave you this problem, and last class I was discussing what is the interval of integration. The first thing that we found, by the way, last class was we found T0. How did we find T0? We found where we found one interval, basically, or the duration of one interval of this signal by looking at 2 points that have similar phase. Meaning, for example, and I gave you the example that I'm going in here, I'm going up, and then right. I need to find, let's say, a part of the signal that is exactly the same phase. Not just because let's say I have a value of the signal equal to 0.5 in here and 0.5 there, this means that this is one period. No. A period is not defined by the difference between 2 points at which the signal is equal to the same value. The phase is defined as how much shift, if I take this thing and copy it and move it to the left, and in fact, let me do this. I don't know if it will work or not. Okay, control copy, control. Okay. I've made a copy of it. Now, if I put it under itself, okay, this is basically the 2 copies of the same signal. How much do I need to move that signal to get it to overlap with itself? Let me move it in here. Now it's overlapping with itself. I have moved it by half a second. 1 second. 1.5. 2. 2.5, 3, 3.5, 4, 4.5, 5. Now, clearly, it didn't overlap perfectly because I sketched it by my hand. But if it was sketched by a computer and it was accurate, you see that the middle period in here overlaps and all of the other periods should overlap. But I needed to move by 5 seconds. So clearly, the period in there is equal to 5. So T0 is equal to 5 seconds. From T0, I can find omega 0. Because if you notice the formula that I have there, the integration has both T0 and omega 0. So I need to find both. Omega 0 is going to be equal to 2 pi divided by T0, which is equal to 2 pi divided by 5. Okay? So we found the first step. The next thing that I was talking about yesterday is what is the area of integration, or what is the duration of the integration? The integration is not from minus infinity to infinity, but it's over one complete period. And here comes an important point. I stressed on it yesterday before the quiz, but maybe I was not able to explain it very well. Always find an interval, one complete period, in which the starting point and the ending point will reduce the complexity of the integration. Sometimes, if you just go and select from 0 to 5, for example, you'll find that the answer will be perfectly correct, but you'll be doing more work than you need. If I ask you, for example, if I ask you to find the area under the following curve, and we'll probably work on this later, but I'm just interested in finding the area under this curve. Now, one way of finding the area, let's say the area in one period, find the area in one period. Okay? You have one of infinite number of possibilities. You can either start integrating one period from here. Let's say this is 1, this is 2, this is 3, this is 0, this is -1, -2, -3, and so on. Okay? To find the area under one period, I assume that I told you that T0 is equal to 2 in here, or you found it. Okay? You can always start the integration from 0 all the way to 2. This is one period. But what's the problem with doing this integration? You'll have to integrate this, assume that this is equal to cosine. Cosine something, okay? This is a shifted version of that first one, okay? So this is going to be equal to cosine, the same thing, -2, because it's shifted by two units to the right. If you wanted to find the area under one period, you can certainly integrate this thing between 0 and 1, and then integrate the second one between 1 and 2, which means that you have 2 integrations. But if you thought about it a little bit smarter than that, and you said that, okay, clearly this area in here is equal to the area in there. So why should I integrate from 0 to 1 and then integrate another function from 1 to 2, which means I'm doing double the work? Let me just integrate one of those functions from -1 to 1, and I'll get exactly the same answer. The same concept holds for the Fourier series. Don't cut an interval into two. If you notice, if you integrate from 0 to 5, you'll cut this interval in here. Let me just highlight it. Let me erase this yellow in here. If you integrate from 0 to 5, you will cut this interval in here. You see this yellow line there? You cut it into two halves. One half, you take it in here, and the other half will appear in there. One half at the beginning of the interval, and the other half at the end of the interval. Trust me, if you just start integrating from -0.5 to 4.5, the effect of this region in here will appear in there. So you'll not lose anything, you'll not gain anything. Clearly, you'll gain the simplicity, but you will not lose anything at all. And this is why I was suggesting, for example, that you do the integration from -0.5 to 4. I remember yesterday when I asked, one of you suggested, and his suggestion was also valid, let's do it from -2.5 to 2.5, and I'll do this one. Okay, Juan? So now we are ready to do the integration. Okay, just give me a minute. One of you has raised his hand. Father Faisal, yes.
Doctor, I have a question.
Father.
Is it right to go from the period 0? I meant the same example you just raised.
Going from -0.5 to 4.5, you mean?
No. The red that you draw.
Oh, sorry. The one that sorry.
Yes, from 0 to 2. Can I say the integral, but I multiply it by 2? Is it the same?
That's okay. Yes. Yes. In this situation, it is okay because I'm only interested in the area. Thank you so much, Faisal, for pointing this out. Okay. In fact, I'm extremely thankful for you for pointing this out. Okay. You see, if you are only interested in the area, yes, what Faisal mentioned is absolutely right, because this area that I have shaded in here, or let me even do it this way. Let me just shade it for you in yellow. You see this area that is shaded in yellow there? You see, this is, by the way, the good thing about using a computer for giving the lecture or having the lectures online. If you were sitting in front of me in the class and I erased the board and then one of you had that question, I wouldn't be able to undo. Okay. So the question is, will I be able to, if I'm asked to find the area under that graph, to just say that, let me find the area of the yellow and multiply by 2? Yes, absolutely. Thank you so much for pointing this, Faisal. You're absolutely right. You would be able to do this. But you would not be able to do this in the Fourier series. And the reason why is that the Fourier series is not a simple integration of the function. You're not just saying, let me integrate. I have cosine, for example, omega t. Let me just integrate this from 0 to 2, for example. This is not what we're doing in the Fourier series. In the Fourier series, we have the function multiplied by e to the power of -j k omega 0 t. If I didn't have this part, dt, if I didn't have this part, yes, you can integrate this part from 0 to 1 and multiply by 2, or from 1 to 2 and multiply by 2. Yes, you can do it. But because I'm multiplying it by a function, another function, I will not be able to do that. You will only be able to do that if it happens that the function in here, this, for example, was doing something like this in here, and was doing exactly the opposite of it over there. Something like this in here. Again, let me maybe emphasize it. You see, if you have two functions, gentlemen, okay, let me do it maybe in blue. If I was doing the integration of the original function, the cosine, yes, I would be able to split it into two halves, or do the integration, let's say, of 1/2 and multiply by 2. But the problem here is because I'm multiplying by an exponent, only if this other function, the other function that I'm multiplying by, was, for example, a constant over the whole interval. Yes, I'll be able to do that. Or if it was doing something like this, it was kind of symmetric, doing something like this in here and doing the opposite of it there. Yes, again, I'll be able to do it. But this exponent is not doing any of those. In fact, this exponent has different function, let's say different shape, over the two halves, here this half and this half. So you cannot do it. If you do it, you'll get the wrong answer. But trust me on this, what that exponent is doing in here, in this interval that I'm shading in here in blue, is exactly what it is doing in here. Exactly the same shape. Okay? So it doesn't make any difference. If I take that function, the x of t, multiplied by that exponent in here, or take the same x of t multiplied by the same exponent in there. Both of those two regions, gentlemen, this region in here and this region are exactly the same. Whether I add to the Fourier series, let's say I have done this integration from here to here. Whether I add to the integration of the Fourier series, this integration from here to here, I add to it this interval or add to it this interval, it will give me exactly the same answer. Okay? In fact, I could even skip both of those if I have, let's say, if I already have what this integration here and this region there is equal to, I can add it to the integration of the Fourier series over there. And for example, I can say that I have the integration of the Fourier series in here, and let's say someone gave me the integration of this interval in here, this one that I'm kind of circling around, I can add it to this, it will give me exactly the same answer. Okay, Juan? Okay. So I hope that this point is very clear. And sometimes, by the way, you see, in exams or quizzes, I'll never give you a function that is maybe that complicated. Why? Because this function contains 3 intervals that I'll have to integrate, as you see. 3 is too much. Usually, typically, in an example, in a quiz or an exam or so, I'll give you maybe 2 intervals. And if you need to integrate, at most, it's going to be 2 intervals, maybe even 1. But selecting the appropriate interval will result either in reducing your work, let's say, by 1/2 or complicating it by double. And either you integrate 1 interval or have two integrations. And sometimes it makes a big difference. If you have only 1 integration, that's 15 minutes. If you have 2 integrations, that's 30 minutes. Why go and spend 15 additional minutes that are wasted? Yeah, this is basically what I'm trying to say. Okay, Juan? طيب. So now let's do the Fourier series. تفضل أحمد.
Yes, Doctor. How can I identify the best suitable interval in order to integrate?
How can you identify what? Your
The
voice
best
was not
interval. You have mentioned that choosing the right interval will integrate for easy.
Okay. Let me say it this way. It doesn't. There are probably infinite number of possible good answers. I suggested, for example, from -0.5. Let me select the green in here. Green. Okay. I selected from -0.5 to 4.5. One of you selected -2.5 to 2.5. Both of those are good. Why? Because if you notice, in the interval that I selected, which is -0.5 to 4.5, the function has 3 levels. If you think about it, the function changes from a value of 1 to a value of 2, then to a value of 0, then to a value of 0.5. If you select the interval that I selected, which is this one, okay, you'll have the exponent multiplied by 1 in here, added to it the exponent multiplied by 2, added to it the exponent multiplied by 0.5. 3 different intervals. Think of it this way. If you look at the other suggestion of your friend last class, it contains exactly the same 3 regions. This one, let me do it in maybe orange. This interval here, which is the exponent multiplied by 0.5, plus the exponent multiplied by 1, plus the exponent multiplied by 2. So again, 3 integrations. Someone else could say, let me go from -3.5 to 1.5, which is this interval, which is exactly the same. You see, in fact, this interval is exactly like 2.5 to -2.5 to 2.5, because it happens that this interval here, this region there, let me highlight it. Let me zoom in. You see this interval here from -3.5 to 2.5, the function was equal to 0. So in fact, I could start from any point in that interval. I can select any point between -3.5 to 2.5. For example, -3. But the important thing is that I have to end at 2. If I start at -3, I have to end at 2. Okay, which is somewhere in here. There. Okay. The important thing is that always select intervals in which you do not break regions that you have to integrate into two halves. Again, let me just emphasize it. Yani, the following starting points are good. In fact, I'll do them maybe in green. Sorry, the function turned out to be a mess. Any of the green intervals, gentlemen, are good. Any of the green intervals are good intervals, are good starting points. In here, in there, in here, in here, in here, up to this point. All of those starting points are ending 5 units later. Okay? And wherever you start, you have to theoretically end 5 units later. Okay? Any of those points are good. This is bad. So let me do it in red. Bad. Sorry. Change color. Change color. I'm not able to change the color. For some reason, it's not changing color. Hold on. Okay, I'll do it maybe. What can I do? Like, let me see. Let me try to maybe erase something there, maybe to fix things. I don't. Sorry, this computer has been driving me crazy lately. Let me. Okay, I don't change the other pin, but that's okay. The green points or the green starting points are okay. This is bad, 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 bad. Why? Because if you start at any of those points, you're leaving a little bit there that you need to complete from the other interval. You see this part that I have left in here, you'll have to complete it in there, which means that you'll end up with another integration. Yeah. I don't know if I can change this now to maybe green. Change this back to green. Okay. You see those? Good, 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 good. Okay. Again, let me change it to red or pink or whatever. Yeah. Bad, 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 bad. Okay. Unless you have this point. You see this point in here, 0.5? 0.5 is good. Because 0.5 happens to be between the level at which this signal is equal to 1 and the level at which it's equal to 2. So if you start at that point, it's okay. It's true. You have left all of this out, which means that you'll take it in the other interval. Okay? But please do not leave part of the interval, part of an interval where the function is doing something, and take it in the other interval, because it will complicate your life. Okay, Juan? I hope that now it's clear.
Yes, yes.
Okay, good. Right, so let me go now to the function, and I have messed up the function a little bit. I don't know where the axis is. Okay, the axis was there, somewhere there. Sorry, I have to switch the colors from here. Okay. Right? So now let's do the integration. Remember, the x of t is equal to 1 over t0, the integration over one interval. And let me write this interval. What is the interval? Let me take the minus 2.5 to 2.5. 2.5 of x of t multiplied by e to the power of minus jk omega 0 t dt. Now this is the formula. I just plugged in in fact, let me just come in here and plug in the value of t0, which is equal to 5. And wherever you see omega 0, replace it with, I think, 2 pi over 5. Okay, something like that. Okay, so this is basically the integration that I have to do. Now, clearly, the x of t is not constant, or is not defined as the same function over the whole interval from minus 2.5 to 2.5. We said that we have to break this integration into several regions. And this is the beauty, or this is the idea of having the appropriate, let's say, limits of integration. So clearly, I have to break this into 3 intervals. And they're 3 because I have selected the minus 2.5. So this becomes equal to 1 over 5 times the integration from the first interval is minus 2.5. This is, by the way, minus 2.5 here. Minus 2.5 to minus 1.5 of x of t. What is the value of x of t in this interval? It's 0.5. If I remember correctly, I think this was equal to 0.5. Right? In fact, just for the sake of argument, let me make it 1. I think 0.5 is going to add a fraction there that I'm not interested in. Yeah? Let me make this 1, let me make this 2, and let me make this 4, for example. I could have done it with the 0.5. It's just that I wanted to make it a little bit easier. So 1 over 5 times the x of t in that interval, which is equal to 1, multiplied by e to the power of minus j, k, 2 pi divided by 5 t dt. Okay, this is the first integration. Second integration, 1 over 5 integration. Now clearly I have also to integrate this over this interval. Let me highlight it. You see this? I cannot change color. Cannot change color. Okay, you see this interval in here, the one that I'm pointing to. Theoretically, I have to integrate. I have to take that function x multiplied by the exponent and integrate. It just happens that the function over that interval is equal to 0. So forget about it. You get rid of it. Okay? It makes your life a little bit simpler. So plus the integration from minus 0.5 to 0.5 of what is the function in that interval? It's equal to 2. So multiplied by 2, multiplied by e to the power of minus j, k, times 2 pi over 5 t, and the last dt طبعا. Okay. And the last integration plus 1 over 5. The integration from the third interval is from 0.5 to 1.5 times 4 times e to the power of minus j, k, 2 pi over 5 t. Okay? This is basically what I need to do. Now you can think of it, by the way. Okay, I was going to say something, but maybe it's not time for it. Okay. Now those are the 3 integrations that I have to do, and I'm going to do them. The integrations, by the way, if you notice them, they're almost all the same, except that I have in here a constant, another constant. Okay. So once you do one of the integrations, the other integrations are quite easy. Now I'm one of those, by the way, who like always to have the limits, if possible, of the integration to be positive. I think, in my opinion, having the limits of integration being positive, sometimes it makes it a little bit easier, but it's up to you. Meaning that I could have started, for example, from 0.5 to 5.5. By doing this, all of the limits of integration will become positive. But it's up to you. This integration is perfectly okay. Now let's do the integration. So what am I going to have? I'm going to have the 1 over 5. The 1 is a constant. I can take it out, but it's 1 anyway. Okay. Now what's the integration of e to the power of a t dt? Remind me. What's the integration of e to the power of at dt? تفضل عبد الرحمن.
So 1 over a e to the at.
Exactly. Okay. The integration of any exponent, gentlemen, is always you divide by the coefficient of t in the exponent. Whatever the coefficient of t, all the coefficient of t, everything with minus signs, with k's, with whatever. All of this is considered to be the coefficient of k. You divide by it, multiply it by the same exponent as it is, and substitute the limits. So clearly this becomes equal to e to the power, let me divide by 1 over the whole coefficient of t, which is minus j, k, 2 pi over 5. All of that is the coefficient of t multiplied by e to the power of minus j, k, 2 pi over 5 t, evaluated from minus 2.5 to 2.5. No, sorry, to minus 1.5. Okay, this is the first integration. Let me, in fact, I'm feeling a little lazy, to be honest. And because I'm using a computer, yeah, so I can do this. Control copy, Control V. Control copy. Not just plug it there. You see how easy it is if you're using a computer. Control V. What I need to do is just change. In here I have 2, I think. Change this to red. In here I have 2, and there I have 4, and I have to change the limits. 4, and this is 2. The limits in here for the second one are minus 0.5 to 0.5, and the limits for the last one are 0.5 to 1.5. I don't need the last plus sign. Now let's just do substitution. Now in here, by the way, for this function, it's not going to be really illustrative. In fact, I'll tell you what I'll do. Inshallah, next class, what I will do is we'll get a result here. I will sketch this result next class on MATLAB. I should have done it maybe earlier. And I solved this problem, okay, at home, but maybe it didn't cross my mind to sketch the to sketch the Fourier transform of the signal, the Fourier series, of the signal, and show you the signal along with its Fourier series and show you that they match, okay? But inshallah, I'll try to do it maybe later today and show you the result tomorrow, okay? But let's get the result now for the time being and see what happens, okay? Notice that all of this, without the 2 in there, all of this is a constant. Sorry, I don't know what's happening to me today, okay? All of this is common for all of the terms, so I can take it out. So this becomes equal to 1 over 5, 1 over minus j, k, 2 pi over 5. And from the first one, I have e to the power of minus j, k, 2 pi over 5. By the way, my handwriting is a little bit terrible because the computer is standing up, and I have to do it this way because I have a fan. I told you yesterday that I'm having a problem with the computer, so I have a fan that is cooling it. If I lay it down, I'm sure that it will heat up. So my apologies for the handwriting, for the bad handwriting. But I promise, inshallah, that I will solve this, inshallah, problem in the lecture notes later, and you'll have it available. So, and substituted at this.
The exam, do you have to evaluate or just write the final expression for the integral?
What do you mean? I didn't get your point.
يعني يكفي نكتب الاكسبريشن اللي فوق ولا لازم نسوي evaluation?
Okay, I'll tell you. For example, if I ask you to find the Fourier series, okay, the point that I'm going to reach there is sufficient. Okay, just give me a minute. I'll tell you. This is basically what I expect you to have. Clear? Okay, just give me a minute. So e to the power of minus jk, okay, minus e to the power of minus jk, 2 pi over 5, substituted at minus 2.5. Plus, and I'll repeat this for all of those terms. So I'll have to substitute, the whole thing here has been taken out. I'll have to take this, multiplied by 2, so 2e to the power of minus j, k, 2 pi over 5, multiplied by minus 0, sorry, plus 0.5, minus 2e to the power of minus j, k, 2 pi over 5, plus, sorry, minus 0.5. Okay, plus, and so on. And there will be some 2 terms. Basically, this is, if you reach this point, you have evaluated the Fourier series. Now, so most likely, if I give you a problem in which I ask you to find the Fourier series, reaching this point, you get the full mark. Unless there is another thing that we need to do with the Fourier series. There are specific situations in which, gentlemen, I'm interested in using now the Fourier series for doing something else, as you see, inshallah, later, probably in the next few classes. Okay? In this situation, it's not enough to reach this point, but you probably need to simplify. What do I mean by simplify? If you notice, all of those exponents have common terms. In fact, I have, for example, I can take probably, if I give you, or let me say it this way. Depending on the function itself, you might find that some of those exponents can be combined together into a single function. And we'll talk about this function, inshallah, later on when we talk about something called the sinc function. But if the question says the following, given this signal, find the Fourier series, and you find this, you get a full mark. Okay? However, if I ask you to sketch, for example, the result, The problem with sketching this is that it's not easy. Or sketching a signal like this is not easy. And I'll have to struggle with it on MATLAB. Now, I'm expert in MATLAB, so I'll probably be able to do it. But there are some situations in which you need to simplify the signal. So reaching this point will not give you the full mark. But when we reach this point, we'll talk about it at that. We'll talk about it at that point. But at least for the time being, in this example, reaching this point, this means that you have evaluated the Fourier series. Okay? Did I answer your question?
Yes.
Okay, good. طيب تفضل براء. براء, you have a question?
Yeah, sorry, just it takes time to open the mic.
No problem.
What about the value of K?
Okay, the point in here is the following. Thank you for pointing this out. In fact, this also comes to the question of that Ahmed has mentioned. Okay, should we stop here? Now, what you did in here is you have evaluated the Fourier series. Meaning, for example, me, if I'm your boss, let's say, in a company, and I wanted you to evaluate the Fourier series so that I take this Fourier series and do something with it, I'll take this, plug it into a program or so, plug in different values of K, and I'll come up with a plot. This basically is the Fourier series, period. Now, if you wanted to do some more work on, if you wanted to use the concept of the Fourier series to get more insight on what the signal is, clearly you'll have to evaluate this for different values of K. In fact, what I wanted to do after that is I wanted to evaluate it at K equal to 0. You remember what K equal to 0 meant? Let me go back to the functions in there. Which term has K equal to 0? Out of those C's. Remember, by the way, sorry, by the way, my apologies. Hold on. Sorry. In here, I kept writing x of t. This is ck. Sorry, this is ck. My apologies. For some reason, you see the formula in here says ck. I don't know why I was writing x of t. Okay. What we found, gentlemen, was ck, was not x of t. My apologies. Yeah. What we found in here, my sincere apologies for this. This is ck. This is ck. And this is ck. Those are the coefficients. This is not the function. My sincere apologies for this. Okay. So what we found were the coefficients. Now my question to you is, what is, if I plug in k equal to 0, what does that represent? I'm going to get clearly C0. What is that C0 in here? If you look at the term C0, what do you notice about it? It's this term, isn't it?
Yeah.
It's a constant, which represents the DC value of your function. In fact, C0 is always called the DC value or the average value of your function. We know that any sine, let's say, for example, the average of a cosine is equal to 0. The average of a sine is equal to 0. But the average, for example, of cosine squared is not equal to 0. The average of sine squared is not equal to 0. Generally, if you have any periodic signal, it will have an average that is not 0. Some periodic signals have an average that is equal to 0, but not all of them. In fact, the average of the periodic signal that you're trying to represent using the Fourier series is equal to C0. Let us plug in C equal to 0 in there. Now, the problem is that plugging in C equal to 0 in there is going to cause a problem. Okay. What will happen if you plug in C equal to 0 in here? Let's come to this formula and plug in C equal to 0. What do you think will happen in here? I'm not going to do the whole thing in here, okay? But if you plug in K equal to 0, I'm sorry, not C equal to 0, K equal to 0, what will happen? We're going to get 0 in the denominator, okay? How am I going to say it in here? Okay. If we plug in, gentlemen, K equal to 0 there, we're going to get something that is undefined, okay? But trust me on this, later on, inshallah, when we talk about the Fourier transform, you'll see that in signals that look like this, when you plug in K equal to 0, you're not going to get something that is undefined. Yeah? We will use something called L'Hopital's rule, which is, I think you have studied it in math, to be able to find what is basically the limit of this quantity when K is equal to, when K basically approaches 0. Okay? But basically what I'm trying to say, gentlemen, is that when we plug in different values of K there, K equal to 0, K equal to 1, and so on, we will get those C's in there. The different C's that we have in there, C1, C2, and so on, will be obtained when we plug in k equal to 0, k equal to 1, k equal to 2, and so on. Yeah? In fact, if we wanted to find C0 there directly, without getting it from this formula, and trust me on this formula will allow us to find what is C0 if we plug in k equal to 0, but we'll have to do another step that I think you're not ready for at the time being. Okay? If we wanted to evaluate this formula for the value of k equal to 0, all we had to do is just do the integration there right away without this exponent. You see, if we just remove this exponent, when you plug in k to be equal to 0 in this exponent in there, this exponent becomes equal to 1. And now when you do the integration will give you the same thing in there without this, and with a lot of the components that you have in there basically disappearing. Okay, a lot of the components that you have there will disappear. In fact, I think this will become equal to 1. This will become equal to 1. This will become equal to 1. So we'll end up with some of the components in there. Okay, and you'll basically be able to get what is the average value of that x of t, or basically what is C0, which represents the average value of this Fourier series. Okay, so anyway, I'll leave it at this point. I need to solve another example, another Fourier series, and I promise you that we will come to this point later. Okay, when we talk about how do we use the Fourier series, and what is the benefit of the Fourier series. Okay, I promise you that we'll come to this inshallah later. Right? Let me give you a second example, which is slightly more complicated, I think, in my opinion, than the example that we have there. I think so. Right? What is that example? The example is the same thing that I have there. I'm not going to erase this because I need it so that at the end I can write the, I can include it in the lecture notes. Yeah? But the following, this is the example. Yeah? So this is a second example. Yeah? Find the Fourier series. Okay, find the Fourier series expansion, let's say, of x of t, which is given by the following function. You remember the function that I sketched a few minutes ago, which is called rectified cosine. So like this. Now this seems to be easier. It's easier in one aspect, but it's more difficult in another aspect. And let's say that this is equal to minus 3 to 3. So this is going to be 9. This is going to be at 6. This is going to be 15, and so on. Minus 9, minus 15. Okay. And let's say this is equal to 2. So this is x of t. So what I'm asking you here is find the Fourier series expansion of this. And find the Fourier series coefficients, let's say. Find the c's. And once I get the c's in here, I'll talk about finding other Fourier series coefficients. You remember we talked about 3 types of Fourier series. We talked about the trigonometric and the combined trigonometric. I'll work on the other 2 from this one. I didn't want to do it for this example because it would be very difficult for this example. So now let's do this. Now again, for this example, we need to find T0. How much is T0? This is quite simple in here, in this situation. How much is T0? Anybody? Follow Muhammad.
T0 is 6.
Absolutely 6. Okay. How do you know? You can take 2 peaks, for example. Okay. Now, 2 peaks, clearly the peak in here is going to be somewhere in between the 3 and 9, which is 6. Okay. Or easier than that, take those 2 points from here to here. This is again 1 period. Now notice this, by the way. Cosine, this is, I expect you to find this, but if I told you that this is a rectified cosine, you should be able to figure out what is the function in here. What is this function? In fact, let me ask you this. I wanted to say something, but if I say that, it will reveal for you the something that I wanted you to find. Okay. Now, if we wanted to do the integration there, if we wanted to find the Fourier series, I'll have to plug in what is x of t. Now, I didn't tell you what x of t. If you notice in the example, I told you find the Fourier series of x of t, where x of t is given by this, where x of t here is a rectified cosine, meaning a cosine that is passed through an absolute value. Can anyone tell me what is that cosine? What is the function of that cosine? The period was equal, or T0 was equal to 6. Now, from T0, we can find omega 0, right? What is omega 0? 2 pi over T0, isn't it?
Yes.
Yeah, Tafadhal, Muhammad. You want to say this?
Yes, yes.
Okay, 2 pi over 6, which is equal to, okay, 2 pi over 6, whatever it is, okay, which is equal to pi over 3. Now, here's maybe the thing that probably will trick some of you. We wanted to find x of t so that we can plug x of t here multiplied by the exponent. Clearly, you cannot plug a plot in the integration. You have to find what is the formula for x of t. Now, what is x of t? Do you think that x of t is equal to cosine omega, which is equal to pi over 3t? Do you think that this is equal to the cosine? I'm sorry, is this equal to x of t? Fadal Abdurrahman.
No, we need to multiply it by 2.
Absolutely, you're absolutely right. Okay, notice this, gentlemen. In fact, you need you need to multiply you need to divide the frequency by 2. Okay, you see, here's the trick, gentlemen. If you want to think about it as a trick, I told you that this is a rectified cosine. Maybe I didn't write it in the question, but let's say that I told you in the question, I want you to find the Fourier series of this rectified cosine, and all I gave you is the plot of the cosine, which means that for you to plug in x of t in this formula, you need to come up with x of t. Now, x of t does not have a frequency which is equal to the frequency of that signal. Why? Let me sketch the cosine that resulted in this rectified. And after I took the absolute value of it, I ended up with this. Would you agree with me? I hope I can change colors now. Okay, yeah, now I can change colors. Would you agree with me that this, and let me make it a little bit thicker. Would you agree with me that the cosine that resulted in this rectified signal is this? So sorry for the sketch, it's not accurate. But would you agree with me that this is the black curve? If I take the absolute value of it, I end up with the red curve. Now, the red curve happens to have a period which is equal to 6. But the black one has a period which is double that. So the period, in fact, of the black one is 12. And this is the frequency, or let's say from that period, let me call it Tx. The period of the signal x is equal to Tx, which is equal to 12. Which means that omega x will be equal to 2 pi divided by 12, which is equal to pi divided by 6. So in fact, the cosine that resulted in this rectified cosine is not equal to cosine pi over 3, but it's cosine pi over 12. Now you may say, why do we have discrepancy in the frequency or in the period?
Over 6, Doctor.
Sorry, yeah, over 6. Yeah, thank you so much. Over 6. Yeah, thank you. Okay, over 6. So why did we have the x of t having a period that is equal to 12, while the rectified cosine having a period that is equal to 6 only? It's because when you take the absolute value of a cosine, the negative values become positive. And now you have let's say, think of it this way. The original cosine was repeating every 12 seconds from here to here. But because I flipped this negative part, it became positive. And now I have more periods of the rectified cosine. The rectified cosine has higher frequency compared to the original cosine. This, by the way, phenomena happens also when you square a signal. When you square the cosine. For example, if I told you, what is the frequency of this signal? Cosine 2 pi 5t. What is the frequency of this cosine? It's 2 pi 5, isn't it? Or 10 pi. Agree with me? What is the frequency of cosine squared 2 pi 5t? Anybody knows what is the frequency of this cosine? If you plot it, what is the frequency of it? It's going to be double this frequency. If you don't know this, it's going to be double this. In fact, it's going to have a frequency which is equal to 2 pi times 10, or basically 20 pi. Now you may say, how come? It's a cosine. What did the squaring do to it? The squaring did something similar to the absolute value. In fact, we know that cosine squared can be written as 1 plus cosine, double the frequency, or double the angle, which is cosine 2 pi times 10 t divided by 2. This is in fact equal to this. So in fact, if you plot this one, this is exactly what you're going to get. You're going to get a cosine that is shifted up by 1/2 unit because of this, and it has a frequency that is doubled. This is exactly what the absolute value did to that cosine. It increased the frequency to double. Okay? Right. So this came to my mind, and we'll use this inshallah later in the future. So I thought I'll just mention it. So in fact, my x of t in here, x of t is equal to, or let's say x of t in there is equal to cosine, we said pi divided by 6t. Yeah? Now I'm ready to plug in the x of t in my formula. Yeah? So the integration, and we said that we need to integrate over one period, and it makes sense to integrate from -3 all the way to 3, not from 0 to 6. Because if you integrate from 0 to 6, this means that you have to integrate this, which is equal to cosine pi over 6t, and then do another integration for this part, which means that you're going to end up with 2 integrations and double the work. And certainly you'll have also to find what is the function in here, which is going to be a shifted version of this one by a value that is equal to 6. Okay? So let's do the integration from -3 to 3. So clearly the ck is going to be equal to 1 over t, t0, which is equal to how much we said t0? 6. 1 over 6. The integration from -3 to 3 of cosine pi over 6t multiplied by e to the power of minus jk k omega 0. Omega 0 is equal to, we said, pi over 6. Sorry, yeah, pi over 6. Pi over 6t dt. Okay? Okay, so we've come up with the integration. Let's just do the integration. Now, who can integrate for me here? What's the integration of cosine multiplied by exponent? Anyone knows?
I think by part.
Okay. What Abdurrahman said is absolutely right. The problem is that integrating by parts in here will probably take you, you know the integration by parts, right? Anyway, okay, trust me, I will never give you an integration in this course that requires you to integrate by parts, okay? Maybe we'll solve a problem, but I will never give you in a quiz or in an exam any integration that will require you to integrate by parts. So we agree on this. Why? Because I'm afraid that if I give you any problem in which you needed to integrate by parts, that you're not going to be able to integrate, not because you don't understand the concept, the electrical engineering concept, but you're not going to be able to integrate because integration by parts is something that you took 2 years ago and it's difficult and so on. So you mess up the problem not because of the electrical engineering, but because of the math. And I prefer to give you a simple problem that I test you on the concept of the, let's say, EE207 concepts, rather than giving you a problem in which I test you on the math. But I'm telling you that this does not require you to integrate by parts. There is a trick that we can do that will allow us to do the integration without integration by parts. Abdurrahman, I think you raised your hand. I'm not sure. You had a question, or did you want to say this?
Yes, I think we can use Euler's formula.
Exactly. Okay, we can use Euler's formula. You remember a long time ago, somewhere up in the lecture notes, we mentioned that a cosine and a sine, if you add them, cosine x plus j sine x, this becomes equal to e to the power of jx, or j. Let's say j theta is equal to cosine theta plus j sine theta. This is a formula, although it looks complicated, or let's say it's kind of okay. But believe me, in many problems that we will be working in this course, this formula is your friend. In fact, this formula tells you what is the exponent in terms of the cosine and sine. But we can also use this formula to represent the cosine and sine in terms of complex exponentials. And this is going to be our friend, as you'll see in a minute. Okay. In fact, let me just plug in, and instead of theta, plug in minus theta. So e to the power of minus j theta becomes equal to cosine of theta and cosine of minus theta are exactly the same. So this becomes equal to cosine of theta, minus j sine theta. This is nothing but the complex conjugate of this. and the complex conjugate of two numbers in rectangular form, and the representation in here is a rectangular form, is you change the sign of the imaginary part. So we've changed the sign of the imaginary part there. Yeah? Now, let me just add those two, and you'll see the trick, let's say, or the thing that I wanted you to know. Let's just add both sides. If you add both sides, in the in the right-hand side, the imaginary part disappears because we have j sign and minus j sign. Okay. By the way, maybe I skipped a point in here. Let me just show it to you so that you know where it came from. If I plug in e to the power of minus, or let's say j minus theta. Okay. If I just remove theta and plug in minus theta, this will become equal to cosine of minus theta plus j sine of minus theta. Maybe I need to do it in 2 steps. Now, sine of minus theta is equal to minus sine theta. So I can take the minus sign that is inside the angle, change it to a positive sign, and bring the minus sign outside. Okay? And cosine of minus theta is just equal to cosine of theta. So I can remove this minus sign. And the minus sign that I have in there, I can just put it to the front. So this becomes equal to minus j theta. Okay? Now let me add, and this is basically how I got the second formula. Okay? So let me add now. So this part will disappear, and I'll end up with 2 cosine theta. And 2 cosine theta will become equal to e to the power of j theta plus e to the power of minus j theta. Let me just divide by 2. And that's basically the formula that I'm interested in. This is some other form of Euler's formula, by the way. It's not something new. It's just another form of Euler's formula. So now let's use this concept in here. Now, it looks like we're complicating things. We're taking a cosine, converting it to complex exponentials. No, we're not. Because once you convert this into complex exponentials, we know that complex exponentials, you can easily multiply them by each other, right? I mean, when you have, let's say, two exponentials that are multiplied by each other, what do you do to their exponents? You add them. So, and you see that once we add them, we'll end up with something that is, relatively speaking, easy to integrate. By the way, now it just came to my mind that Abdurrahman, when he said use Euler's formula, Abdurrahman, did you mean that we need to convert this into cosine and sine?
No. If we convert it to cosine, we will need the trigonometric identities and all
okay.
that. Yes.
Yeah, you're right. Okay, but if this is what if this is what some of you thought, you could also do it without integration by parts. But in this situation, you need trigonometric identities. You will need to know what is cosine times cosine, and what is cosine multiplied by sine. Okay, so you can do it both ways, by the way. But both ways will get you to avoid having integration by parts. Okay. I personally prefer you change the cosine into complex exponentials rather than you change the complex exponential to cosine and sine. But if you do it both ways will be okay. Right? So we've done this. So let me just erase everything that I have there. And let me just erase this also. Okay. So now the next step will be to write this. So this becomes equal to, by the way, I think my computer, the screen I told you last time, it's starting to vibrate. Now I see honestly everything in the computer fuzzy. And الخطوط بدأت تداخل مع بعض. Let me hope that I can still see what is going on. So this becomes equal to 1/6 multiplied by the integration. Why is this line thinner? So it's equal to 1/6 times the integration from -3 to 3. Let me convert this using that formula. So this becomes equal to e to the power of j pi over 6t plus e to the power of minus j pi over 6t. And the 1/2 that I had in the formula, I'll take it outside, so it becomes 1/12. Okay? and all of this is multiplied by e to the power of minus j k pi over 60. Now, as I mentioned, it looks like we have complicated things, but we didn't. dt. Let me just rewrite this a little bit better, in a better way. So this becomes equal to 1 over 12, the integration from minus 3 to 3. Let me open those parentheses. So I'll end up with e to the power of this, multiply e to the power of this multiplied by e to the power of the other. And we know that whenever you have the product of two exponents, you add the exponents. And basically you end up with e to the power of the first exponent plus the second exponent. So let me take j, common factor outside, and I'll end up with pi over 6t minus j. I'm sorry, the j I already took it outside, minus k pi over 6t. Something like this. Yeah? This is the first term, and the second term plus e to the power of exactly the same term, except that I have a minus sign in here. So I'll end up with j. I'll leave the minus sign inside, so I'll end up with j minus pi over 6 t minus k pi over 6t. In fact, I can take the t outside in both terms. I think it will make it a little bit easier. T and t from here and from there. T. I think I didn't make a mistake. Hopefully, okay. I think I'm fine. Okay, dt though. The whole thing there is multiplied by dt. Okay. So what comes next? Now you can do the integration. You see, no integration by parts, nothing. Okay. So let me do the integration. This is over 12. Let me do the integration. So I'll end up with 1 over 12. The integration of the first, again, everything that is multiplied by t, take it as, this is the coefficient of t, so divide by it. So we'll end up by 1 over j pi divided by 6 minus k pi divided by 6 in here. K, okay, multiplied by e to the power of j pi divided by 6 minus k. Yeah, now it's just, automatic. I mean, you're not doing much. It's just you're trying to do the integration, evaluated. Let me write it this way, from minus 3 to 3. This is the first integration, or the first component. The first, not the first integration, but the first part of the integration. Plus exactly the same, and I'll just copy it. Just to save myself a little bit of time. The difference is that I'm going to end up with, I noticed that whenever I do copy and paste, sometimes OneNote refuses to change to the pins. Let me just maybe minimize it, maximize it. Okay, yeah, no. Okay. So the only difference is that I have a minus sign in here. Difference, this minus sign that I'm, yeah. This minus sign is the only difference, which means that I'll end up with a minus sign in here and a minus sign there. Okay. Evaluate now. I'll have, there's a t, by the way, there. There's a t in here. You see, sometimes even I make mistakes. Now, what remains is to take the 3, substitute there, take the minus 3 and substitute there. 3, substitute there, take the minus 3 and substitute there. Okay? So, I think I'll stop at this point. What I will do, inshallah, hopefully before next class, is I'll solve both of those two problems in an organized way in the notes. And next class, I'll come with the evaluation there, and we'll see what we can do with it. I'll show you basically how we can get the different coefficients, how we can get the A's and B's and so on. And I'll work on this solution here further, but inshallah next class. Okay, Afan? If you have any questions, please go ahead. If you don't have any questions, I'll see you tomorrow. تفضل عبد الرحمن.
هل في الاختبار بيكون فيه formula sheets, something like this?
خلاص, let me think about it. Probably there are some formulas that I'll give you, yes. And I don't want you honestly to memorize some of the formulas that. Let me think about it. Inshallah tomorrow I'll give you an answer. Okay? Inshallah. تفضل محمد.
دكتور ليه قلنا
عفوا محمد الجاري فيرست. تفضل محمد.
ليه دكتور قلنا الاوميجا 0 تساوي باي اوفر 6؟ ليه ما قلنا انها تساوي باي اوفر 3؟ لان التي نود يساوي 6.
Sorry, hold on. I hope I didn't use the incorrect one. Yeah, sorry. My apologies. Yes, you're right. In fact, it's pi over 3. عفوا لحظة. Yeah, I think I confused the two. Hold on, let me see. T naught is equal to 6. I think I'm fine. Okay. T naught is equal to 6, which means omega naught, which I'm gonna plug in here. Yeah, you're right. I confused things. Yes. This should have been, my apologies for this. This should have been pi over 3, not pi over 6. Yes, you're right. In here it is pi over 6. You see in here, this is pi over 6 because this is the cosine that resulted in the function. But in here, this is omega 0. And omega 0 there comes from the period of integration. We are integrating from -3 to 3, which means over 6 seconds. So the omega that we're integrating over, let's say, or the omega of the frequency of integration should be pi over 3. So my apologies for this. Yes, this should have been pi over 3. Thank you so much for pointing this out. Inshallah, I'll correct it in the solution. Okay, so this should have been pi over 3, and so on. Wherever you see k pi over 6, it should be k pi over 3. Okay.
طيب يا دكتور الكوساين ليه قلنا الكوساين باي اوفر 6؟ ليه ما قلنا نفس الشيء باي اوفر 3؟
طيب ليش الكوساين باي اوفر 6 not باي اوفر 3؟ لا الكوساين هذه should be باي اوفر 6 لأن look I'm integrating this cosine. Okay, let me ask you this. Maybe hopefully this will illustrate for you the concept. Assume that I gave you a cosine, part of a cosine like this. وقلت لك I want you to integrate this cosine. على فكرة I don't know why let me just zoom in so that you can see maybe the curve better. Assume I gave you, let me zoom in. I gave you a cosine that looks like this. وقلت لك this is part of a cosine. هذا جزء من cosine. Forget about الآن rectified with pi over 6 and so on. I told you that this is part of a cosine. I know that this cosine has a value that is equal to 1 at this point. It has a value that is equal to 0 in here at 3. It has a value that is equal to 0 at -3. ممكن تقول لي what is x of t in here? What are you going to do? The first thing that will come to your mind is خليني أكمل حتى أشوف what is happening, right? I have part of the cosine. So if I complete it, it will be like this, isn't it? صح ولا
Yes. صح.
Okay. Now, طبعا you can continue further, okay? But based on this, what is x of t?
when cosine omega 0 t.
Okay, cosine omega 0 t. What is omega 0?
باي اوفر 3.
يعني before you find what is omega 0, let's find what is the period of the signal, صح?
صح.
Okay, what is the period of that signal?
6.
لا. 6 means from here to here. But
صح.
the period is one complete interval to here, صح?
ايه.
So the period is equal to
القيمة اللي على اليمين كم هي؟
هذه minus 3. اللي على اليمين 3.
لا اللي على يمينها.
هذه قصدك؟ هذه؟
ايه.
اوكي، اذا هذه minus 3 وهذه 3 what does this equal؟ هذه تكون 6 صح؟ وهذه تكون 12 عفوا تكون 9 sorry 9 صح؟
صح.
Or think of it this way, isn't this 1/2 of the period of the cosine? لأن هذه this is the other half.
صح.
Okay. So if 1/2 of it is equal to 6, so one complete period will be equal to 12.
صحيح.
صح? So clearly this cosine has a period that is equal to 12, which means omega 0 is equal to 2 pi divided by 12, which is pi over 6.
حلو. طيب
هذه اوكي ايه تفضل.
الحين هذه فهمت الباي اوفر 6 بالكوساين، بس الباي اوفر 3 باي اوفر 3 في الاكسبوننشال كيف جبناها؟
جود بوينت. الان ليش طيب في الاكسبوننشال هنا ليش استخدم باي اوفر 3 not باي اوفر 6؟ الان forget about the cosine forget about x انسى x موضوع x. كل اللي قلت لك ان you have a function بغض النظر عن what is the shape of that function. I have a function ايش حصل؟ okay. I have a function that looks like this بغض النظر عن شكلها okay which keeps repeating every 6 seconds. This is one half of it, one period of it. This is the second period of it. This is the third period of it. This is the fourth period of it. فلا تربط البيريد اللي حق اللي هو الفورير سيريز exponent مع البيريد of the cosine. Those are completely different things. One of them اللي هي البيريد اللي حق الكوساين came from the fact that if we complete this cosine we'll end up with a period that is equal to 12. But the period for the that we got اللي هي T0 for the Fourier series, we got it from the fact that the signal that we are trying to find its Fourier series repeats every 6 seconds, not every 12 seconds. You got this point ولا لا؟
ايه فهمتها وضحت.
Okay. طيب على فكرة let me tell you something. Trust me on this. We could have used T0 to be equal to 12 not 6. استخدمناها 6 صح؟ كان بإمكاننا نستخدمها equal to 12. بس في هالحالة هذه it will be as if we are thinking in the signal that we are finding its Fourier series okay is not هذا السيجنال اللي الآن معلمة بالأزرق هي signal that is like this. Two of those. لو انك ما انتبهت والله ان قلت مثلا في بالك انه okay we started from a cosine and then we took the absolute value of it فطلع عندنا two positive sides of the cosine. بس ظنيت انت انه okay this does not increase the frequency by a factor of 2. You will have to apply the Fourier series for a signal that goes from here to here. معناه you'll have to do the integration twice or you'll have to have two integrations. One integration اللي هو from -3 to 3 plus another integration from 3 to 9. Not of this طبعا of a shifted cosine of it. يعني بحيث انك تكتب لي cosine pi over 6 t minus I think minus 6 اللي هي 6 units shifted version of it of the first one طبعا multiplied by the exponent and so on. If you did this, trust me on this, the final answer طبعا يعني the process will be double the amount of work, but the final answer that you will get will have terms that can be combined to give you exactly the same final answer that I got from here. Okay محمد؟
اي وضحت. الله يعطيك العافيه يا دكتور.
حياك الله. الله يعافيك. Any other questions, gentlemen, or comments or points? Any questions, gentlemen? Those who are still logged in.